Hello Year 10, this is lesson 7 in the 1.4 domestic electricity booklet. Today we are going to be looking at fuses. Now at the top of the page you can see a fuse. There it is. And that is a 13 amp fuse, which means if we look at the fuse wire itself, it will be quite thick. There's the 13 amp fuse wire. Whereas a 5 amp fuse wire will be thinner and a 3 amp fuse wire will be thinner still. We will take a look at various appliances. Will give you their power rating in watts and the voltage used, which is in the UK normally 230 volts. From this information we can work out the current that flows through each appliance and therefore what fuse each one needs. Now, as I've previously stated, the fuses available are 3, 5 or 13 amps. We will be using this equation here, power equals current times time, and we're going to be working out the current, and current is given the symbol I. So if you were to put your thumb over the I, current, I would equal P divided by V. So current is power divided by time. So let's work some of these out now. So here are the appliances: TV, kettle, hairdryer, radio. These are the power ratings or similar power ratings that we've seen before. 187 was for that 5 foot across TV. The kettle I'm going to put at 2000 watts or 2 kilowatts. The hairdryer is going to be at 800 watts. And the radio is the piece of equipment with the lowest power rating at 13 watts. Now the voltage, if any of these were to be plugged in using a 3-pin plug, the voltages of course would be 230 volts. You can now work out the current. I will do it for the first one now, and then I'd like you to have a go at the following 3. So the TV, we want to work out current. It is 187 divided by 230, and that gives me 0.8. 0.81. Can you please have a go at these remaining current readings? Well, here come your answers. 2000 divided by 230 for the kettle. 8.70. The hairdryer, 800 divided by 230 gives us 3.48. And then the radio, it's going to be a small number, this very small current, because it's just not a very powerful piece of equipment. 0.06 amps. So the deal is with the fuse, the correct fuse must be close to the operating current. That's this here, but it can't be smaller. So we've got a choice of a 3, a 5 or a 13 amp fuse. So the TV has an operating current of 0.81. The closest one is 3 amps. 3 amp fuse. The kettle, 8.7 amps. That would blow a 3 and a 5 amp fuse. So the fuse must be the 13 amp fuse. For the hairdryer, we've got an operating current of 3.48 amps. That would blow a 3 amp fuse. And so you have to go to the next one up, which will be a 5. And then our radio has a very small current, 0.06. So a 3 amp fuse would be just fine. Let's move on. Question 1. Why would you not put a 5 amp fuse into a TV that operates at 8.7 amps? The operating current is greater than the fuse, and so this fuse, as soon as you turned on the TV, the fuse would melt and the circuit would be broken and the TV wouldn't work. So nice easy one there. Question 2. Calculate the power supplied to a 5 amp 230 volt heater. It's 3 marks. First mark, find the equation. You find that in the equation sheet at the front of your book. It might not be given to you, so you need to be able to find it. Then I, current, is 5, show the workings, times the voltage, which is 230. You've shown your workings there now, so you're going to get a mark. And then it's an answer. 5 times 230 gives us 1,150, but you need to remember the units. You go all the way back to the beginning. Power is measured in watts. Big W. Question 3. This is an interesting one now and potentially extremely dangerous. Why would you not use a 13 amp fuse in a 2.6 amp hairdryer? If too much current flows, the fuse, which is 13 amps, it wouldn't melt. What might melt? The hairdryer. And what might that cause? A fire. Clearly very dangerous. And then question 4. Calculate the current flowing through the toaster and which fuse would you use? Well, hires, you'd have to be able to rearrange the equation. Foundations, the equation rearranged would be given to you. That's the equation. Now the workings. Power 550 divided by the voltage 230. We've shown the workings. Now we want an answer. And we get this 2.39. Current is measured in amps. So there's the first 3 marks, and then it says which fuse would you use? Look at the operating current and look for the fuse which is closest to it but above. We're going to use a 3 amp fuse. Finally, the difference between alternating current, called AC, and direct current, which is called DC. Let's go back to the first one. Alternating current is one that continuously changes direction. Mains electricity is an AC supply, and you can see here that the current is changing direction. At this point here, it's 0. And of course, it's going up, down, and then moving the other way. So it's moving up and down, up and down, up and down. It's a cycle. And it's changing direction continuously. In fact, UK mains electricity is supplied at about 230 volts, and it has a frequency of 50 cycles a second, or 50 hertz. In other words, the current changes direction, flows one way and then the opposite way, or one way and then the opposite way, 50 times a second. Now, direct current has a constant direction. It only flows in one direction, and batteries and cells provide that. And when this is supplied, and you can see the battery right here, and here is a DC supply. There it is on the screen here. It's just a flat, straight line, totally different to alternating current. Now, each cell in a complete circuit provides a PD, or voltage, of 3 volts. So we've got one cell here, number 1, and we've got a voltage. There's the line for number 1. This is because it's DC, it's direct current provided by a battery or a cell. We've got a voltage of approximately 3 volts. There's 0 volts. There's plus 10 volts. Now let's have a look at number 2. We haven't got one cell, we've got 2 cells. So the line that I'm going to attempt to draw now is going to be not 3 volts up, but 2 lots of 3, which is 6. So it's going to start about here, and it will go straight across like that. So we're going to label that up as that is number 2. That's number 2. And the final, no, the penultimate one, we've got the batteries turned round in the other direction. This is number 3 now. So we've got minus 3 volts, add another minus 3 volts. We're going to end up with a voltage that is minus 3 minus 6. So it's going to start about here, move straight across, bump. It's not perfect, but it'll do. And that is your trace, your voltage trace for number 3. Your voltage trace for number 3. Now, we all know that batteries eventually run out of power. They become flat. What will that line look like over time? I shall do this in green. We're going to start off at 3 volts, which is going to be here, and then over time it gets less and less and less until the voltage becomes 0 and the battery is completely flat. So number 4, this is line number 4 here. It started off at 3 volts, which is that point there, and over time it goes down and down and down and down until it reaches 0 volts. Now, the final section. What type of current does this wave trace show? This is AC, alternating current. How many waves can you see? Well, what I'm going to do here is, how am I going to do this now? Here is one wave, 2, 3, green is 4, red is 5 waves, green is 6, red is 7, green is 8, red is 9, and the green is 10. So we have got 10 waves there. Now, how would the trace on the screen change if you increase the frequency of the supply? If you increase the frequency, there'd be more waves. So you would see more waves. The frequency would increase. In actual fact, the wavelength would decrease. It wouldn't be this long. It will be much thinner, much thinner, much thinner. And the final section of this, what would happen to the peaks and the troughs if we were to change the PD, the voltage, from 50 volts to 36 volts? The height of the peaks and troughs would decrease. So they would no longer be up to there like so. It would be a much smaller wave, so the height would be less, the trough would be less as well. Okay, that will do for today. Well done.